Welcome to Study Loop.
Hello everyone, today we're doing chapter 17, problem 16. And this problem asks us to draw the product form when 1,3,5-cycloheptotriene with a pKa of 39 is treated with a strong base. And why is the pKa of this molecule so much higher than a pKa of cyclopentadiene? This one down here. So what is a pKa? So pKa means that at any pH that is less than the pKa, so any pH value that is under 39, then this molecule is going to be protonated. At any pH that is higher than the pKa, this molecule is going to be deprotonated. And why is that? Well, lower pH means that there's more protons in solution. So if there's more protons in a solution and if it's under the pKa value, that means that it's a proton-rich environment. So that means that your molecule will exist in a protonated form. But now if the pKa is higher, that means that we're in a proton-poor environment now, so less amount of protons. So because it's a proton-poor environment, we're actually going to rip off one of these protons to make the environment gain some more protons, so it's happier. So now what happens? Well, we have a strong base and we have these acidic protons. We know that this base is going to rip off one of these protons. This is going to give us an anionic product. And carb anion now with 2 lone pair electrons. And why is this pKa so much higher than this molecule down here? Well, let's determine about aromaticity. So remember, an aromatic compound follows Huckel's rule of 4n plus 2 pi electrons, n being any positive integer or 0. So in the starting material, we have 1, 2, 3, 4, 5, 6 pi electrons, but this molecule is not fully conjugated here because it's an sp3 carbon here, so this is not an aromatic compound in the starting material. Well, what about the base? Well, the addition of this lone pair electron, it actually makes this molecule conjugated because now this lone pair electrons exist in the p orbital, so it can be delocalized around the ring and be contributed to aromaticity. But now this formula, we have 1, 2, 3, 4, 5, 6, 7, 8 pi electrons. 2 from each of these 3 double bonds and 2 from these lone pairs, so 8 pi electrons. So this actually follows the 4n rule, where n equals 2. So we have 4 times 2 equals those 8 electrons. So the 4n rule is actually the rule for anti-aromatic compounds. And anti-aromatic compounds are very, very, very unstable. So because the conjugate base of this molecule is highly unstable, the pKa must be very high such that in most conditions, in most biological conditions, the molecule exists in its protonated form, such as this. Being anti-aromatic, even though it's fully conjugated, being anti-aromatic is highly unstable. So it prefers to being a mildly conjugated, not fully conjugated, and non-aromatic compound than something that's anti-aromatic. Well, what about this molecule? Why does this one have such a low pKa? We can say the pKa of this is going to be around 10, just for this example's sake. It's probably not that actual value, but we'll just say that for the sake of this example. So once again, this base is going to rip off this proton. Now we've created a compound that is not only conjugated now, because now it has these two pi bonds, these 2 double bonds here and here, but now this lone pair electron is involved in the p orbital of carbon, so it actually be involved in delocalizing around the ring. So because of that, now we have 6 pi electrons in the conjugate base, and now that actually follows the 4n plus 2 rule where n equals 1. So we have 4 times 1 plus 2 equals 6. So now our conjugated base is aromatic, and not only that, it's fully conjugated. So this is a very stable anionic conjugate base. So therefore, the pKa is going to be much lower. So then, in most cases, the compound will exist in its anionic deprotonated form. Then its protonated form here, which is uh, uh, not aromatic, and it just has 2 levels of conjugation here. Here it has 3 levels of conjugation, and it's aromatic, so this conjugate base is highly more stabilized than its original protonated counterpart.